So let's start with the first part of the course, first chapter, chapter 1, introduction. So in this chapter, we basically want to understand what is the RF framework. For today, we don't do anything like no definition. We basically try one example, which is on multi-armed bandit, and that one is kind of very famous old example in this domain. So let me just start with a bit of definition. Do you know David Silver? Homework, next session, everybody should know David Silver. David Silver is the guy who was the head of the team, one of the heads of the team in DeepMind, who have developed AlphaZero. You know, this is a kind of breakthrough in deep reinforcement learning. So the machine which can play chess and go, right? And that one is that one is the one which uses deep learning to do reinforcement learning. So he defines reinforcement learning to be the art of decision making, okay? And that totally makes sense. Of course, you can say anything here, and I'm gonna put it there because that's David Silver, right? So that's totally okay, but if you want to just define it from the eyes of a beginner like me, I would call it, this is all about that you learn how to interact with the environment. So what do I mean by that? In the problem of reinforcement learning, in this framework, you always think of such scenario. There is one guy, which is the agent, right? You can think of it as a robot, you can think of it as a human, anyone. And that agent is interacting with something that we call it environment. This means that there is something else that is not under our control. It has its own physics, it has its own rules. And then the only thing that the agent is able to do is to interact with this one. So it's going to make some actions. This is what David Silver called decision. So you're going to do some action. The agent does the action. And once it does the action, the size of the particular action to do, that action is going to impact the environment, right? If I don't know, if I throw some dice on to the sky, then it's gonna rotate and then it gonna turn down, right? So the whole thing that is happening there is not really under my control. This is the gravity and other things in the environment, right? So once it does its decision, it does the action gonna impact the environment, and the environment is going to give it back some reward, right? So it's going to tell the agent that you did that action, this is the kind of prize you get out of your action, right? So that diagram you see here is the whole diagram that we are going to deal with through the semester. So one agent trying to interact with this environment, and what does it want? It wants to make this reward as best as possible. So it's going to collect as much rewards as it can. Now, if you look at this problem, some of you might come with this question that this is not the typical sort of machine learning thing that we had in mind, especially if some of you have had, supervised learning right now in your mind. So in supervised learning, we always have a bunch of inputs and one output, and we want to find out what is the function connecting these two together. But here, the problem is quite different, and that you're totally right. As I told you before, this framework is totally different from the classical other kind of machine learning problems. So many people, when they want to somehow give a very high-level categorization of the topics we have in machine learning, they are somehow breaking it into the supervised, unsupervised, and reinforcement learning. So there are lots of problems in machine learning, for instance, generative AI. And that one, for example, is somehow lying under the umbrella of unsupervised learning. But reinforcement learning, it has its own category because this is not very similar to many things that we have in machine learning. So what are the key differences here? I'm going to explain them, but why we call them, why we call it learning, why we call it reinforcement learning, because what we are doing at the end of the day, we're still trying to learn something or a kind of pattern out of the data that we're collecting from the environment, right? So the best example is always playing some game. And then when you are playing the game, you always have the environment. That environment could be your opponent, or if you're playing the computer, it's the computer, whatever the game is. The other side of the game is actually the environment, right? And then you decide on your moves, you do your moves, and each time you do, you're gonna get some, reward, either maybe plus or negative. And then the thing that you want to just maximize that plus, right? You want to collect as much reward as you can. And typically when you start playing, you first don't have any idea, right? So you just play around with that game, you just get familiar with the rules of the game, and you start to build kind of strategy. You play the game, and you see that your strategy is not working, so you improve it, and you keep on going like that, right? So you're still trying to learn some pattern from the environment, and that particular pattern that you are trying to understand from that environment is supposed to somehow give you, serve you well in your goal, which is, getting the most of the reward, right? So since we are doing a sort of observation from the environment, and we are trying to do the best, use the best out of it, or learn some sort of pattern out of it, this is still a learning problem, but this is not a classical learning problem. Now, to understand what are the key differences between this one and the classical learning problems, which I mean the supervised and unsupervised learning problems that you had in other courses, let me highlight them. One thing is that in reinforcement learning, you don't have a supervised problem. The supervision doesn't make really sense. Because what does supervision mean? It means that you have a label, right? So you have a data, and that data has been labeled. But in reinforcement learning, defining the notion of label is quite hard, right? If you're playing chess, what is a good move? Like a move, this is one data that I'm collecting, right? And I do that move. Is it a good move or a bad move? I mean, nobody can say, right? At least at the beginning, right? At some point, maybe towards very end, someone who is expert can say, but very beginning or in the middle, many moves are unclear to us, right? Could be a good move. We don't know what the guy has in mind. It could be a good move. It could be a bad move, right? So the notion of supervision is not having any definition here, because the only thing that you have is not, you really don't have a true label. You just have a reward from the environment, right? And that reward could be extremely sparse. Like you play with the chess and you wait for, many moves till you get your final reward, which is whether you win or you lose, right? So that is one thing here. The other thing is that the notion of data set here. So the kind of data set that you have in reinforcement learning is not the kind of conventional data set that you had in other learning problems. So in classical, say, supervised learning problems, you always have a data set collecting a bunch of inputs and their corresponding label, right? You get that, and you try to train your model, right? But when you are doing reinforcement learning, you eventually can build your data set out of interacting with the environment, right? So I'm going to decide on my move. I move, I'm going to get a reward, and now this reward is the feedback I get, right? And that one is going to be stored again inside my data set. And then out of this new data and whatever I had before, I'm supposed to just build my next move, right? So in that sense, the data that you have here is essentially somehow expanding through time. You can think of it like this. So your data set is somehow ad hoc in this sense. And the move that you're doing, the decision that you're doing is going to impact the kind of data that you access, right? So if you decide to do this move, you're going to get one sample. If you decide to do another move, you're going to get another sample, right? So the decision that you make impacts the collection of the data, and also data that you're constructing is going to increase through time, right? So this is again different to the conventional approaches that you have. And one other thing that is very important here is that the time really matters in reinforcement learning, right? Why? Why? Because, for instance, say you are playing a game, the chess, right? You really need to do the move, and then you need to wait to see your opponent, and then you decide, right? You cannot decide for the whole strategy right before the start of the game, right? This is impossible. Because if you stick to one strategy blindly, then definitely people are going to find it out and they're going to beat you, right? So this is not possible. Like time is a very important component to the whole process. When you are interacting with the environment, you always need, I mean, this order of the time really matters. You need to just move, you do your action, and you wait for the reward, and out of that, you develop your next action. Okay? So one thing is that, for instance, we have some time-dependent data in classical machine learning, but this one is totally different to them. Okay? So in classical machine learning, data-dependent data is like, for example, a time sequence, right? But this is not that one because you don't have access to the whole trajectory towards the very end, right? You're playing, you're somehow in the online interaction with your environment. Okay, so as I said, the best example that you can always have in mind if you want to think about reinforcement learning is to play a board game. The best one, very complicated, is the chess game. So in the chess game, you essentially start from nothing. And I do know that you can play a couple of times to collect some experience, but let's think of very simple. If I start with chess playing, the first time I'm playing with some new opponent, I'm starting from nothing, right? So I don't know what is the strategy the other side is going to play. I don't know their kind of level of experience. I'm going to just do my first move, right? And then they are going to do their own move. And we'll keep on going. Yes.
Yeah. Just regarding the data set, because we are collecting the data while we play the game, and
yes.
Essentially we're just our best. The best effort we can have is that we just obtain a subset of possible state or possible moves. But in that case, how do you really guarantee the quality of learning?
We're not going to. I mean, as I said, you don't really need. If you think like that, just think about a very simple game. Okay. Think about a very simple game with a very limited space and actions where you can actually cover all the cases through time. But if you're thinking that way, then of course we can build experience. But we are going to talk about this. I mean, this is the whole thing that you need to go through the semester. But my main idea is that if you think about one episode of playing the game, you eventually, through that episode, you're actually increasing the amount of data you have, right? So that one is going again to impact your policy. Potentially it can, right? If you think optimum. And then this is a key difference to the classical machine learning, where you just get those previous episodes and you don't think about anything that you're doing online with the environment, right? So you can, of course, I mean, in brackets, you can, of course, do those approaches on your experience. That is what we call imitation learning, right? But that is not the topic that we're doing here. I'm going to mention it towards very end, and then you're going to see the difference right now. But don't confuse yourself. Right now, this the key difference that one, while we are playing, you are collecting more data, right? Questions? No question? Okay, so playing chess. When I play chess, I start from nothing. If I'm thinking about one episode of playing chess, right? And the only thing that I do know is a bunch of rules, right? Those bunch of rules are eventually a part of my environment. Those rules, the board, the other side, all of them together are the environment, right? And the agent is me who is playing this game, right? Now, when I start playing that game, I start from total nothing, right? I have nothing, no information about the other side. I start doing a move. And once I do the move, the other side is going to do the move as well, right? Now, given the new state of this whole game, I'm going to decide for my next move and next move and next move. And every single move that I do in this episode is going to be somehow impacted by the previous results, right? So this is one point here. The other point is that, okay, the action I already defined it for you. So the action is basically the move that I do in the game. And every single move that I do is based on the observation I do, right? So this observation, they're important, might not be exactly the whole thing on the environment, right? I really cannot read the mind of the opponent, but the only thing that I have access to is the chessboard, right? So I can see the last moves of the opponent, and based on that, I can decide whether optimal approach or best thing to do next, right? Now, if you think about the chess, and you try to somehow match this guy to what I already told you in the other slide, you can now explain the key differences to the classical machine learning approach. So the three differences was, first of all, there was no supervision here. You cannot really define the notion of supervision. Because if you do one move, there is no clear whether this is, you cannot say, nobody can say in chess that this is really a good move or a bad move, right? Because that totally depends on the other side. If you are towards very, very, very end of the game, you might say, okay, this move is not very good because obviously after doing this move, this is giving the chance to the opponent to easily finish the game, right? But it again depends on the other side. Maybe you concluded that the other side is not going to do that, right? Then this is maybe a good move, right? So you cannot really call something good or bad here, right? This notion is not available anymore. This is different from image classification, where one image is really cat or dog, right? This is a different thing. The other thing is that data set is different. So as you keep on playing with the other side, you start to build some mindset about the other side. You're going to see some, trends in the other side is playing. And this is going to increase your information and then improve your policy or strategy in playing that game, right? So this is not a conventional one that you are collecting a bunch of samples and that's it. And the time really matters, of course, because when you want to play that board, the chess, each time you move, you really need to wait for the other side, right? So for example, like when you play with a kid, the kids usually do one, very dummy move. And they think that in the next move, you're not understanding what they're doing. So they get the chance to, put you in a very bad position. But yeah, you're going to understand it, right? So they are not having the notion of time, but that time really matters in that sense. So this example, I just wanted to give you this idea that reinforcement learning is like conceptually different from the classical machine learning things that you had before. And for many people, this sounds more than machine learning. It sounds like a kind of control or online optimization problem. Now, this idea of reinforcement learning, as I told you, has been for a very, very long time in the community of data science and engineering. And one of the very most big, or one of the very sophisticated breakthroughs of the recent time is AlphaZero. So I put you this video, you can click on it and you can take a look at that one. And then you're going to meet also David Silver in that YouTube video. And you're going to see this AlphaZero in case that you don't have it and you have not seen it before. I guess many of you have already seen it. But if you have not seen it, just take a look at that video. So this sort of target, we want at the end of the day to be able to do that, basically to play chess with the computer very efficiently. But for the moment, I'm not going to start at that point. I'm going to start for somehow 70 years ago, when the idea of multi-arm banded problem was there. Okay, so I'm gonna start with this very basic example, which, I mean, we're gonna do it together. You can actually do it at home easily by yourself, but this is going to somehow take you into the environment of reinforcement learning, what you're really dealing with and what is the target.